And also each point is equivalent to a vector. So we can also have a vector of length 2. So if the vector is length 2, it means that it's a vector which goes through. Now, just to remember, so this vector is the same as this vector. They're all the same. We treat them the same. Those are them. And minus is the other. So this is in one-dimensional mode. Everything is nice. Then we go to two-dimensional mode, and it's a little bit different. So now we cannot just say one number because it should be not identify the vector part. So it's even going to solve it. So our board is a two-dimensional thing. The vector of 2 wouldn't distinguish these two. So there are different ways to distinguish them. One way, which would be, I think, the first way to come to mind, would be this. So we define a 0. And we also pick our lines. And then we draw our vector, whatever it is. So if we give out its length and its angle, because any vector that you have, would be, so any vector that you pick, anything here, you just move it here, you just tell its length and its angle, yourself. Okay. So this is called polar coordinates. We wouldn't encounter that much here, just sometimes, I even don't think it is that universal, but sometimes. Now, the second way, which is not the most natural way, but the easy way to work with, is the Cartesian. So in this system, we pick any point again here, x, y, and then you can just, any point would be equal to a vector. Which we assume that the vector is from the origin to the. So again, any point will also distinguish a vector with vector coordinates. Now, so this would be, so these two systems are equivalent, you can change them together. Okay, we really don't worry about it. Now, so after this preliminary, the first thing that you always see is the line. And so, if we have this system and we have a line here, we want to find this equation. So if you remember, the equation of the line was the equation of the line was something else. So let's see where this line comes from. So if this is x, this is y coordinate. So if you look at this point, and if this is 1, then this would be m, and this would be. So this would be telling us that if you have 1 unit of x, how many, if you increase this by 1 unit, how much y would go up, which basically means that you go 1 step ahead, you go 1 minute. And b will tell you where you're starting from. So the equation of this line is y equals m plus 1. I'm just going fast because I assume everybody knows it. Now the first question, which is very simple but people always forget. So if you have 2 points here, x1 and y1, and x2 and y2, what's the equation of lines passing through it?
minus y. Y minus y.
Okay. So some people remember that. I expected more people to remember, but that's so let's see how we find it. So we'll look at this line. This is the line that we really want to find it. So its slope would be the ratio of this guy to this guy, which is y2 minus y1 divided by x2 minus x1. So x2 minus this, y2 minus this. So this would be m. And then this would pass through either this point or this point. Any of them, doesn't matter. So you can write y minus y1 equals this x minus x. So this is the equation of this line passing through. Or you can just write it 2 and 2 here, it's the same. Or even if you don't remember this, it's not really important. You know that the equation of line looks like this. So you write y1 equals mx1 plus b, y2 equals mx2 plus b, and then you know y1, y2, x1, x2, you solve for m and b, find them like a math. So yeah, that's something that you should know. And you'll be surprised how you forget it. Now, the second thing that we want to talk about, okay, that's it. Now we go to 3. So in one dimension, this is a line, then we know what the circle is, for example. Oh, for knowing the circle, we have to know a new property, that's the length of the vector. So if you have a vector which, so from now on, all my vectors will just start from 0, so that I can get rid of this and just give 1 point at the. And so when I say vector xy, it means that it's from 0, 0 to x. So if you have a vector xy and you want to find its length, it's a triangle, 90 degrees, so it would be root 2 plus y2. Okay. Now, the equation of a circle would be all the points that are from the same distance from the origin. But it's not necessarily origin, it's the center of the circle. That's what it's having. So if you have x2 plus y2 equals 8, that is by far. So if we have this, this is the equation of all the points that are in distance r from the distance r from the origin. Now knowing these things, let's go to 3 dimensions. In 3 dimensions, everything just remains the same. Maybe a little bit different sometimes. Just to have a small practice, just think of some 3-dimensional objects and just draw them together view of them. So assume that this is a 3. So any object would have 3 coordinates: x, y, z. And when you don't mention any of them in the equation, it means that it's 3. So if you have an object called z equals 0, what's that object? It's the whole plane. So it's the whole plane, exactly. It's the plane which is at the, its height is 0. It's whole plane. So if you have x equals y, what's that?
It's a 45 degree.
Okay. X equals 5 is, okay, I think that we're looking at the plane, just the plane. So this is x equals. X equals y is this line. Now this line is here, now it goes up and down all the way. So it would be the plane which is perpendicular. Good. So it seems that you know everything again. Just one more and then we're done. So what is this thing? X plus y equals x. I can 25.
Radius at the point.
So it's not a circle, just remember. It's a cylinder. It's a 3-dimensional object, not a 2-dimensional object. So since we're talking in 3 dimensions, this thing goes all the way up. And it's empty. So if it's less than equal to 25, then the cylinder is also solid. It's a solid thing, exactly. So just be careful with this thing. So they can be a little bit tricky, less than equal to. But in this class and everywhere, I think you would mostly see planes and hyperplanes. They're nice. Nothing is circular. These things won't happen normally. Okay. Good. Now let's go to talk about vectors and what we did in the class. last question. So we know about how we define a vector. Well, you have all the coordinates. So, well, vectors. Let me show them with E and U. So vectors that are in the same dimension, both of them are in the plane or both of them are in the space, they can be added together. They can be deducted from each other, and it's just done coordinate-wise. So U plus V, if they are two dimensions, we call them V1 plus U1, and V2 plus V2. This would be adding and deducting them would be exactly the same way. Now, we define something called dot product. So this is maybe the first weird thing that we're doing. So if V is V1, V2, and U is U1, U2, then the dot product would be defined as, so this is just a definition, there is no reason behind it. So this is a definition. That's how we define it. Yeah. Obviously there are some properties just by looking at this. U dot V equals, V dot U equals U dot V, it's the same thing. This is. And then you can also show that it's commutative in the sense that if we have V dot U plus W is equal to V dot U plus V dot W. And now the next thing which we will need is U dot U would be U1 to the power of 2 plus U2 to the power of 2. Which, looking at what we define here as the length of the vector, this would be length of vector U to the power of 2. Okay? I hope that there is no question. Now, by knowing these things, we can prove, it's not a definition anymore, that if you have two vectors, their dot product would be this. Length of the first one multiplied by length of the second one, multiplied by the cosine of the angle. So this is not a definition anymore. This is just a proof. Writing these things down, you can prove it. If you want it, I will do it. But there is no need to prove that. So then we can prove that if we just do this, we'll get it. Now there is something nice here which you might like to know. So if you have two vectors here, this is U, this is V. One quantity that sometimes we are interested in finding is the length of the projection of this guy and this guy. And so we want to find this length. This is the length of the projection. So knowing the properties of the dot product and knowing a little bit of trigonometry, you know that, let me just throw it here. So if this is U, this is V, this is the projection. If this is theta, this length is equal to U cosine of theta. So we know that from trigonometry. Now, knowing the dot product, if we just bring the V part here, you're all set. So if you have two vectors and you find the dot product of these two, and then divide it by the length of one of them, you will find the length of the projection of this one and the other one. That's something that sometimes might be helpful. It's not really a big thing, it's just bringing this guy down. So this would give you this one. If you have a major in physics, you have used this thing. Now that's the only thing about matrices which I wanted to say, maybe a little bit in addition to what we had in class about vectors. Now let's go to matrices. Really exciting. So in matrices are defined exactly like vectors, and just put some of them in each other. Nothing really fancy. So I will define my matrix A11 to A1M, AN1, and I want to have n rows. This is AMN. Sorry? Okay. So this has m rows and n columns. Normally, the convention is that you use n for rows and n for columns. The opposite. So we just call this guy matrix. Obviously, a matrix is nothing but just some vector put together in a column wise or some vector put together in vector wise. no such thing. Nothing really fancy. Now, we define something called the transpose of a matrix, which is, okay, take this row, make it a column. Take the second row, make it the second column. So the transpose will be written from A11 to A1n, and this goes to AN1 to AN. So then the transpose will be an n by n. As an example, 1, 5, 6. This transpose will be 1, 3, 5, 2, 4, 6. So this is one of the very fundamental, or the basic things that can be made. Now, we call a matrix and a square matrix if n and m are equal. If n and m are, if for a square matrix there's a property called a symmetric matrix. A symmetric matrix is a matrix which A and A transpose are equal. Obviously, this holds only for a square matrix. Because if your matrix is not square, a matrix of 2 by 3 cannot be equal to a matrix of 2 by 3 by 2. It's like comparing lion with elephant. So, now, so a matrix like this would be a symmetric matrix. Because it would look like this after me. Basically, a symmetric matrix, if you look at the main diagonal, things here as the mirror. Now, this is also one thing that we need. Then we also need some, well, you know how to multiply matrices. Everybody knows. So I wouldn't go over that one. Just we should remember that if you multiply matrices, assume that there are 3 matrices that you're multiplying, so you multiply these 2 and then by this, it is equal to this here. So this is good. Now this is important to know that A multiplied B is not necessarily equal to B multiplied A. This is something that first of all, if A multiplied B is defined, B multiplied by A might not be defined or might be defined. Assume that this is a 2 by 3 matrix, this is a 3 by 1 matrix. Then this one is not even defined. But even if it's defined, that let's say it's this. Even if it's defined, this is not necessarily equal. So we cannot do it. But we know something nice, which sometimes might be helpful. If we have 2 matrices which are multiplying them and we take the transpose, then it will be B transpose. This one we know. And getting them is extremely easy. You should just write down the 2 matrices and multiply them and do it the other way. That's the proof. The proof is just pick 2 examples of matrices, do it, and then say this is we can generalize it to any other thing. And this is my first page of knowledge. Now we define some property for any matrix called its determinant. That we don't go into detail like what it is. Let's say it's a number associated with our matrices. And you can calculate it easily, but I don't know, you really don't need to know how to do it. So, for example, for a 2 by 2 matrix, A, B, C, D, its determinant is A, B minus C. Okay. And this number is used in finding the inverse of a matrix. So let's see what the inverse of a matrix is. If you have a square matrix A square matrix A minus 1 is defined to be a matrix that when you multiply these two, the result is the identity matrix, or something like this. So when I write matrices like this, 0 with a bar over there, or even no bar, just 0, it means that everything here is 0. Now, if a matrix has determinant, but this is for 2 by 2, we can define it for any square matrix. If its determinant is 0, it does not have an inverse. If it's non-zero, it has an inverse. Now, for example, so some matrices is easy to calculate their determinant. If you have a matrix like this, which all the above of the diagonal is 0, then the determinant is just multiplying the numbers on the diagonal. So the determinant of this guy, I, is 1. Now, there is one property that you should know. If you have 2 matrices which are multiplied, their determinant, if these are square matrices, because determinant is only defined for a square matrix. So if, for example, this is 2 by 2 and this is 2 by 2, then determinant of AB equals to determinant of A multiplied by determinant of B. And something, so from this one and this one, you can show that determinant of A minus 1 equals determinant of A multiplied by determinant of A minus 1 equals determinant of I, which equals 1. So you know that the determinant of these two guys are inverse of each other. And that's it. Oh, there's one more thing. Determinant of A equals determinant of A transpose. And the last thing to know is that if you just switch a line, if you just switch these two lines, then the determinant would change its sign from multiplied by minus. And think of determinant something like this. If you remember in normal, when you're solving an equation, these are numbers. Ax equals b, then x equals a to the power of minus 1, then a is not equal to 0. That's when you're solving an equation. Now, if you have a system of equations, we call them ax equals b, which is nothing more than this. Equal x1, x2, which is just equivalent to writing a11 x1 plus a12 x2 equals b1 and a21 x1 plus a22 x2 equals b2. So this is just writing it in the matrix format. So we want to solve this thing. We call this xb. So this gives you x equals a minus 1b, but instead of having a is not equal to 0, this is not enough, we should have determinant of a is not equal to 0. So determinant kind of plays the same role here that, just a equals to 0. That's what we should know about determinants, and I think that now let's go to, so this was some really preliminary stuff I can show you all. Now, our next step is going to talk about derivatives a little. Just recall all the rules. And see what we have. So, assume that we have a curve in 2 dimensions. I'm going back to 2 dimensions. Again, everything is 2 dimensions. Now, this is my curve. And I pick one point, we call it P. And I take a second point, we call it 1. Now, there's a line going through. So, this line would have a slope. So if we call this, I call this guy x0, I call this guy x0 plus 1. So the slope would be, so our line is passing through these points, x0 and f of x0, and x0 plus h, and f of x0 plus h. So my line is passing through these two lines, these 2 points. So the slope would be nothing more than f of x0 plus h minus f of x divided by divided by x0 plus h minus x0. This is what we did just 10 minutes ago when we were writing equations. So this, which you can simplify to h, this would be the slope of this line. Now, we define the tangent to be, so let's bring this line Q from Q, very near to this guy, so this line would look like this, and at some point, when it's pretty near that, we change to this line, we call it the tangent. It's the line that only crosses the curve at one point. Intersects the curve at only one point. It's really bad. So now we are interested in finding the slope of that line, which when we draw that line, it only intersects the curve at one point, and not 2 points. Right? We call that now. So what do we do for finding that? We have to make, take this guy here. So we have to take the limit of this ratio when h is going to 0. So this would just turn out to be a simple limit calculation. So let me see. I think let's do a simple example. So we have this curve, and we want to find the tangent. So this curve looks like this. Now at point 1, we want to find this. Okay. So let's see how we do it. We just use the definition. So it will be limit of f of 1 plus h, because I'm looking at x0 equals 1, minus f of 1 divided by h, and h goes to 0. So this will turn out to be 1 plus h, 1 plus h to the power of 2 minus 1 to the power of 3, because f of x equals this, divided by h, which equals to 1 plus h, h minus 1 divided by h, h goes to 0, limit, this guy with this guy, so it will turn out to be limit of 2 plus h, then h goes to 0, which gives us 2. So the slope of line which is tangent to our curve is 2. So the equation of that line would be, well, we have a line with slope 2 which passes through the point 1, 1. So the equation would be y minus 1 equals 2 x. So this will be the equation of the line which is tangent to our curve. Now, this is the hard way of finding the derivative. We're finding that slope. Now, people have come and found all these rules, nice rules, to generalize these things, to find, instead of taking the limit always, memorize some rules. So all these rules that I'm going to write down, their proof is you have to write down the same thing, take the limit, but then instead of putting 1, you will just put x, 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 so at the end it will be a function of x. Nothing to do with that. So let's look at those. I'm not sure which ones I want to. So a lot of functions look like this. Yeah, these nice functions that we also. Now their derivative, which I would show them by f prime of x, is r x to the power of r minus x. Just exactly the same thing. Go ahead and do this. What do you really want? Now we can look at some more strange functions. Okay, let me see. Now, so one thing that you should bear in mind, sometimes the derivative doesn't exist. What does it mean that the derivative doesn't exist? It means that this limit doesn't exist. Okay? Let's look at one case that this limit doesn't exist, and say why it doesn't exist. So look at this thing. F of x equals absolute value of x. Looks like this. Or you can even look at the function like this. Really doesn't. So if you look at these two functions, let's see what you see. This one is easier to look at. At this point, if you write down all those guys, nice thing, and if you take the limit, at the end it would turn out that the derivative would be limit of absolute value of x over x and x goes to 0. This would turn out to be f prime of x. But then this guy doesn't have one value. If you are getting near to x from the positive value, this is equal to 1. But if you're getting to x from the negative value, this would be minus 1. So the limit doesn't exist. So we define two new notions. Limit when something is going from the right side or something going from the left side. Okay. Now we say the limit exists if these two are equal. In this case, limit of this guy when x is going to 0 plus equals 1, but this one equals minus 1. Since they are not equal, we say the limit doesn't exist. So by existence of this limit, I mean this. Of course, there can be other cases. It can go to infinity, then you can just say existence, but we don't worry about it. So there are cases that the limit doesn't exist. But still, you can write that, for some rule of thumb, sometimes you might need to. But the derivative doesn't exist only at this point. At other points, the derivative exists. So if my function is this, its derivative would be 1 minus 1 when x is 2 greater than 0 when x is 3 greater than 0, and at 0 is not. That's it. Now let's look at derivative from a new point of view. Just let's go back to this guy and this definition. If we show this guy the difference in the y coordinate and this guy the difference in the x coordinate, this was the slope of the line, our line. Now, there are different notations for derivatives. This is another notation. So we call this thing, this is exactly just writing the same thing that I wrote. So instead of f prime of x, I will call it this. You can think of, they are not, but you can think of these guys as small changes in x. So this is a small change in x, this is a small change in y when x is changing a little. But they are not independent. That's really important. In fact, you can write it like this. Let's say, think of it like this. Okay. Then we define this guy to be f prime of x. That's what we did just a second ago. So dy equals f prime of x dx. So what does this mean? This means that if your x changes a little, then for that little change, your dy will change by this amount. That's some kind of approximation that you would use a lot later on. So if, for example, your curve is a real line, then this is exact. So if you change a little, then this guy exactly would go up by the derivative, because the derivative is the slope. But if your line looks like this, then a little small change, and then you are a little off by that. Depends on how much your curve is bad. Then you will see that you will just continue this more and more and get something called Taylor expansion. So this is also some nice things that you should remember. Now some very, very general rules of derivative. So if two functions are added and you're taking the derivative, it's just like taking their derivative separately. Well, these are a little conditions in there, but you really don't need to worry, For example, there might be a part in this one and this one which makes them non-differentiable, and then you add them, they just go out. So this is different from that. But for all the nice functions that we know, these guys hold. So you can just... And their proof is like that, exactly like that. If they are multiplied, I'm going to give a nice example of this one. We do it that way. If we have an inverse of a function, its derivative would be minus f prime divided by f to the power of 2. And you also have f over g prime, it would be f prime g minus g prime f divided by g. So these are g and f are just functions. So these are some properties that you definitely know. And just for that multiplication, I'd like to picture something you would like to have a look at it too. So assume that our looks like so you have f multiplied by g. So assume that this is f and this is I'll let you know. Assume this is u and this is their function of x. So when they multiply, this is the area of this rectangle. Okay. Now we want to find the ratio of delta UV to delta X when X equals 0. Okay? So let's see what's delta UV. Delta UV means a little change in U and a little change in V. So we have a little change in U, and we have a little change in V. You really don't need to write it. I'm just going to give you some intuition on what's happening. So this part would be delta U, delta V. This part would be delta V multiplied by U. And this part would be V multiplied by delta. So this is the area of this guy. This is the area of this guy, this area of this guy, and this is just U. Okay? Now, so delta UV would be the amount of, if we change X a little, this guy change a little, so this is delta UV, the part that we're looking at. So delta UV would be nothing more than delta V multiplied by U plus U multiplied by delta V plus delta U delta V. Now we want its ratio over delta X. Delta X, delta X. Now take delta X to 0. So, I'm just going to skip, not going to skip. So look at this guy first. Delta U, delta V over delta X, and delta X goes to 0 is V prime. So V prime U, whatever. Then look at this guy. Delta U, delta V over delta X is U V prime. And then look at, I drop them, doesn't matter. Look at this guy. It would be U prime multiplied by delta V when delta X goes to 0. So this is itself, this is itself. When delta X goes to 0, delta V also goes to 0. So this would be 0 multiplied by a number. We assume it's not infinity. This goes to 0. So derivative of UV, which is this ratio, would be equal to V prime U plus U prime U. This is not a real proof. This is just a sketch of what's happening. Just to show what this guy is. Well, this guy just means that you can evaluate that. Now, these are certain rules that you should know. This part is something that you should know by heart. And I'm sure you know. Now, the last thing about derivatives that you need to know is the chain rule, which is something very useful. I'm sure you've heard the name. So, if you have the function f of a function of x, so let's see what this means. Assume that g of x is equal to root of x, and f of x equals to sine of x. Now, so f of g of x would be nothing more than sine of root of x. So that's what f of x is. So derivative of this type. So there are two ways to calculate the derivative of it. Just write it explicitly and then take derivative of this guy using that definition, which makes your life hard. Or you can just remember that the derivative of that guy is g prime of x multiplied by f prime of g of x. Now to make my life easier, I make this guy 2. Really try to make it easy. So, what's g prime of x is 2x. What's f prime of x? Does anybody remember what's the derivative of the sine of x? Cosine of x. So the derivative of sine of x is cosine of x. So multiplied by cosine of g of x, which is x cubed. So this would be derivative of this x. So this is something that you should remember, that f of g of x is derivative equal to g prime of x, f prime of g of x. That's it. For example, we can think of this guy. We want to take the derivative of this guy. Let's think of it this way. Assume that f of x equals 1 over x, and g of x equals x to minus 4. So now this is f of g of x, so the derivative would be g prime 2x multiplied by derivative of this guy. This guy is x to the power of minus 1, its derivative would be minus 1 x to the power of minus 2. This is just using the fact that x to the power of r is derivative in r x to the power of minus 1. So then, this is multiplied by minus 1. Now, So this is x, this is the g prime of x, and this is the f prime, but we need the f prime of g of x. So minus 1, x to minus 2 to the power of minus 1, x to the power of x to minus 4 to the power of minus 7. So this would be the result. So what I did, I distinguished f and g, then take the derivative of x, and this is f prime of x, but f prime of g of x. So f prime instead of x, I have to substitute g. This can be a little bit complicated sometimes. Maybe 10 functions, f of g of h of w of x. Just go ahead with it. Now, just to refresh your mind, because I said this thing, remember that sine of x, its derivative is cosine of x. Cosine of x, its derivative is what?
Minus sine x.
Minus sine of x. Good. And tangent of x, you don't need to memorize it. I don't know really. But we know that it's sine of x over cosine of x. You know this, and you also know something that I deleted, that f over g prime is f prime of g minus g prime of f. Or it would be done actually something called secant of x, which is 1 over cosine, but really don't need to memorize it. So knowing these two is enough to calculate anything. We don't do that encounter in that question. Now we have something that you might have forgotten from the calculus. So who remember something called mean value theorem? Good. It seems that there is something new for you. Or you just didn't tell me, I don't know. Something nice. I think it's very intuitive, I'm just... Now, okay. If you're traveling from city A to city B, and it's, let's say, 300 kilometers, okay? And you start at 1 p.m. and get here at 3 p.m. So let's see what was your average velocity. It was 300 divided by 2, 150 kilometers per hour. It's a little bit fast, but that's really good to understand. Now, you are sure that at one point, when you were traveling from here to here, your speed, at least at one instance, was exactly this number. Why? Because if it was always less than this, then the average would be less than this. And if it was always more than this, the average would be more than this. So at some point here, at some point, at least at some point, it was exactly 150 kilometers per hour. This is one of the manifestations of something called the mean value theorem. If you remember from your physics, if we had the distance, the derivative of the derivative of the distance was the velocity. The speed was the derivative of and the derivative of the velocity was the acceleration. So this is something, now let's go back to our setting. If you have a function, f, which is satisfies some conditions, those conditions are that over a closed interval, I forgot to mention this one. So do you know what this means? This is a closed interval. So if a point is here, it means that x is less than equal to this. And there's something called an open interval, which you write it either this way or you write it this way. Which these two mean this is a string. So over a closed, if you have a function f, if you have a function f, which over a closed interval ab, it is continuous. Right? And differentiable, this one I remember quite like it. So if it's continuous and differentiable over this closed interval, then you are sure that there exists a point called, can everybody see this one? fp minus fa divided by dA. This is just this line, the slope of this line connecting these two ends, you are sure that there is one point C belonging to AE, which the derivative at that point is equal to the slope of this line. So in this case, C is somewhere here. This picture is up. So you are sure that there is one point here, which the slope at that point will be equal to this. This is called the mean value theorem. And if you remember yesterday, we used this line called, this is called this for every. Then there is also this line called there exists. So there exists a point C, which C is between A and B, and derivative of F at that point is equal to this slope. This is called mean value theorem. It has a lot of things in proving a lot of stuff, but we just, maybe it's not that much practical, but we try to use it to show something. Okay, before going to using it, I just want to make sure and just point out that these two things are very important. It should be differentiable and it should be continuous. If you violate any of these conditions, this would happen. For example, if it's not continuous at its somewhere not in the end, AB, somewhere in the end, it would be something like this. I have to look at my picture so that I don't remember the pictures. But I think your function looks like this. Okay. Now, this would be your the line connecting endpoints, but none of these guys here would be tangent. Or if it's not continuous at the endpoint, a function like, you really don't need to remember these examples. I just want to show that it's important. Assume that this is your function. So this is point A, and just at point B it's not continuous. Just pointing something here is so this will be this, which none of the tangents will be equal. So it's important to be continuous at every point. And it's also important to be differentiable. Because if you have this, assume this goes to infinity. This is where that goes to infinity, the tangent is. Now, this would be the line, and none of the derivatives will be. So if it's differentiable, and if it's continuous, then there exists a point C, which is comfortable. Now, let's see how this can help us. Sometimes this will give us really nice inequalities. Okay? You might use in doing stuff. For example, we can prove using this that sine of x is always less than x. This might sound a little bit weird. Let me just look at my house. Now, if x is greater than 2 pi, x is in radians. Okay. This is obviously greater than 1, which is greater than sine of x. You don't need to worry about anything. Oh, I'm proving this for x greater than 0. So if x is greater than 2 pi, you're fine. This is proved. If x is less than 2 pi, let's write down the mean value theorem for this guy. So we would know that sine of x minus sine of 0 divided by x minus 0. This is f of x minus f of 0 divided by x minus 0. We know that there exists one point between, let's call it alpha, which is between 0 and x, and sine is continuous and differentiable, which the value of this guy would be sine of alpha prime, which equals to cosine of alpha. Okay? Which is less than 1. Okay? Now, if this is less than 1, we know that sine of 0 is 0, 0 is 0. We know that sine of x divided by x is less than 1. So we know that sine of x is less than x. So we show that if x is greater than 2 pi, it's greater than 10. If it's less than 2 pi, it's slightly greater than 10. So this was one use of that. Now you can also, if you want, I even don't recommend it, but if you are interested, for example, you can prove this. same way, find the correct function, apply this, boom. And this is something nice to know. Sometimes you might refer to not this, but the mean value. Good to know. Okay, now we have the notion of increasing and decreasing functions, which you know, and we also have the notion of non-increasing and non-decreasing functions. So just, when I was learning it, we called them differently, but it's the same. So if x1 is strictly greater than x2, if this results in this guy, we call it that this is a non-decreasing function, because this can remain constant. Okay. So this function or this function, both of them qualify for this. So we call it a non-decreasing function. If it's like this, we call it a increasing function. Sometimes they call this increasing function and then call this a strictly increasing function. Just the name. And the other way around also. But the thing that we want to talk about is, if something is an increasing function, then its derivative is positive. If it's decreasing, its derivative is negative. Of course, I'm assuming a lot of regularity conditions here. It's continuous, differentiable, like solid lines, which you would nearly always think of. I think that's something we talked about in class. Yeah. There's one more thing about derivatives, and then we forget to stop them. And so all of you remember E and ln, these two functions. I don't know how many of you remember its definition. It's not important at all. I'm just going to touch on it and talk about the proper terms. So, I don't know how, but well, there are billions of definitions for that. The one that I like, and I learned it in that way, was this. We looked at the function 1 over x, nothing really fancy, and we pick point 1. Yeah. X. And this is the area below it, A of x. So, we said ln of x equals to A of x if x is greater than equal to 1, equals to minus A of x if x is less than 1. And this function is defined only for polynomials. So this is one definition. You can have billions of other definitions. They are all equal. You take one of them, the others are consequences. So I look at this curve, the area below it, I define it ln of x. Then, forget everything. This was just a, okay. These are what you should remember. ln of x is derivative is equal to 1 over x. It's equal to 1 over x. If you remember, you don't need it. What was the area below a curve? Because it's integral, so this is the same. Now, what is... So like any other function which is 1 to 1, forget it what it is, it has an inverse. We call the inverse of this function e to the power of x. So, for example, if we have y equals ln of x, then we call x equals e to the power of x. It is just inverse of that function. And what you should remember is that e to the power of x, its derivative is itself. In fact, it's the only function which is derivative is itself, plus a constant. Okay? Now, assume that we want to take the derivative of this guy, e to the power of x. So we use what we call chain rule. F of g of... Oh, let's use before that, maybe I need to no. So we want to find the derivative of this guy. So f of x in this case is e to the power of x, g of x is equal to x2. So this is f of g of x. So it's g prime of x, 2x. Now, what's the derivative of this? It's itself. So e to the power of g of x. So it would be this is something else. You would never encounter log of not a, for example, a. They are just depending on number. That would be just confusing. Now, this would be all we need to remember about h. Now let's use them in something called the Taylor function. So let's see what the Taylor expansion. So you saw that if we have a line, we call it, its equation was y equals ax plus b, but later on we found that we renamed this a to n prime. Okay. So basically, we call this f of x. So this is just writing this here. Now, so we can say, that's I didn't want to say. So we call this line this. Now, if you have another function, let's look at it like this. This might be f of x equals the bad drawing, but minus x2. Minus x2 plus. I draw it bad. Now, this one is not like that. You cannot just write the derivative like this. But still, you can do something. At one point, if you draw this line, when you are really near this thing, it's not that much different from the line. So we just approximate it at places near points. Again, the same line. Basically, it's like if you magnify it, we are saying that if we are here, and we want to find the value here. Okay, so this is x, x0 plus epsilon, x small. So I'm just saying there's a value here. If I put this thing instead of this thing, they're not that much different. They're near this thing. So, and sometimes you might like to do that. Why? Because calculating f of x might be really hard, but taking the derivative multiplying by x is very simple. So it makes life simple. Now, for most of the functions, we can find better approximation. This is just a linear approximation. You can find a second order approximation, a third order approximation. So then you are not approximating this curve just with one line, but you are approximating with, for example, this curve. Then you approximate it with another. And then we can show that we can improve this approximation as much as we want. We call this whole story results in something called Taylor expansion. We write it this way. Say f of x equals okay. I made a mistake there. So x0. So plus f prime of x0 multiplied by x. I'm going to explain what since I'm wrong here, I have to not write the wrong thing back. So up to now we have been talking about this guy. Forget that term for first time. So I just said that I want the value at point x. So I pick the value at point x0 and then assume that there is a line passing and approximate this with it. So this plus the value of this. So this will give me an approximation of the value of x. Oh, okay. Maybe by so this is what's happening. This is point x0, this is point x. This is my function. I'm saying that for finding f of x, which is this, I do this. But I know the value of function at x0. So I get f of x0 plus f prime of x0, which is the slope, multiplied by the difference between these two sides. Basically, this line, the point on this line has value. So it would be f of x0 plus f prime of x0 x minus x. So this point is an approximation for this one. Okay? Now, I can better this approximation by using a second derivative. This would be how the second derivative term would look like. So then this function obviously is not a linear function anymore. It's a quadratic function. So this would look like, for example, this, a little bit better. Now I can continue this, use third order derivative, fourth order derivative, and make it better. And for most functions that we know, this will work. You just need to continue. And you are sure you have really good bounds on the error. So the error is not a big thing, you can bound it, everything. Now the general formula for this will be this. F of x equals, I don't think we would ever use this one, 2 terms of this will be the general formula for Taylor expansion. So if we put n equals 0, 0 factorial is 1, 0 derivative is just the same function, f of x, and this is some number to the power of 0 is 1. So all this 1, f of x. For n equals 1, it will be the first derivative divided by 1, x minus x 0 to the power. Second derivative, 2 factorial is 2, x minus x 0 to the power 2, third, and so on. So this is just a Taylor expansion. So the Taylor expansion, its idea is that you're trying to approximate a very complex function. Weird stuff, but you have derivatives, you have all those. So instead of evaluating it, you do this. Now, the next step is going to do. I have something here that I should show you. Now the next step is to generalize all the things that I've been saying in multivariables. Not one thing. Everything was single variable, everything was nice. Now all these things exist in multivariable except for a few small changes. The first thing is to define these derivatives in a multivariable space. So the first thing is again going back to the definition and see what we mean by derivative in non-one-dimensional, two-dimensional. Let's do it. So now our function is f of x, y. Okay, before going to that, you can, by this notion of having more than one dimension, we can have 4 types of functions. We can have functions like this, y equals f of x. So you give it in real number, it gives you real number. You can have a function like this. Y, x, so you give it a vector, it gives you back a number. It can be anything, just sum them, anything. This is one kind of function. There is another kind of function which looks like this. So you just give it one number, and it gives back a vector. It can be an equation of a curve in a 3-dimensional space. And you also can have this. You give it a vector, it gives back a vector. So we are not concerned with this at all here. We are not concerned with this at all. So we just talk about this. So you can forget about this at all. Just wanted to mention that here. So you can just generalize the idea from here to either of these, but we don't need to. So we are in space and we give a vector and we get a point. Now, let's see how we define derivatives here. So we calling it partial derivative. And we write it like this. Or we write it like this. There is a small difference. So when I say put a 1 here, it means that I take the derivative with respect to the first value. Or you just write the name of the first value. This would be limit of I write everything for 2-dimensional vector. x1 plus h into x2 minus f of x1, x2 divided by h. And h will be. So this is what we call a partial derivative with respect to the first coordinate. You can have the partial derivative with respect to the second one defined exactly the same. In fact, when I was giving you that general rules, I was cheating a little. So when I said f of x equals x to the power of r, and its derivative is rx to the power of r minus 1, in fact, its partial derivative is r to the power of x minus 1, because r is one variable, x is another variable. So this is a function of two variables. I assume that this is just a number, so it's basically the same, it's just partial. So partial derivative means assume that any other thing is fixed, there are a number, take the derivative. So this is, in a sense, itself a partial derivative in this way. Now, so if you have a function which has two variables, you have two partial derivatives. If you remember, in the one-dimensional case, if a function was differentiable at one point, it was necessarily continuous. So if a function was not continuous, it was not differentiable. But here, it might easily be that the function has all its partial derivative, but it's not continuous. We can just have it. I can give you an example. If you just want to think of it, I'm not going to prove, you can just write down these things and calculate it. This function, f of x y equals 2xy divided by x2 plus y2, then x, y is not equal to 0, 0, and is equal to 0 when x, y is equal to 0. This function is not continuous at point 0, 0, but all its first derivative, partial derivatives exist, everything is nice. So here you don't have that property, you lose it. So in one-dimensional case, if it was differentiable, it was continuous. But here if it's differentiable, it doesn't mean it's continuous. It can be non-continuous. That's the main mistake that people might make, because it's just something naturally we think that it's differentiable, it means that it's something is true, but it's not. Then we define something called gradient for any of these functions, and gradient is nothing but just a special vector defined in a special vector. So if you have f like that, and we write it either this way, gradient of f or gradient of f, with a vector, which is a derivative with respect to the first one, and derivative with respect to the second. If it's 10-dimensional, first and second one. And the next thing is, so it has some properties which I'm not going to go over them that much. Okay, so for example, this would be the direction that if you go, the most rapid change in the function will happen in this direction. So, for example, if you have a function which is like, good example. And if you look at the topological maps of a mountain, it looks like this. These are the level curves. So this is the tip of the mountain, 1,000 meters, 900, 800. So I assume everybody knows what level curves are. So these curves are just joining the points which are at the level of 800. So if this is your mountain, you look at it from the top and just draw lines which represent the points which are at the same height, it will look something like this. And then if you look at the river goes down like this. And if you just draw it, the gradient is the direction which you have the most change. So negative of gradient is the most decline, the rapidest decline, the most rapid decline. So this is just following the gradient of the mountain. You can just look at it as a function and take the gradient. And at any point, it's just water is going down as fast as it can. That's just a physical representation of it. But in math, it's just the direction that you go, the function changes its value more than any other direction. Then you can define something which you will then go through called directional derivative, which will tell you, okay, in this direction, the rate of change is this much, in the other direction, the rate of change is whatever it is. No, it's not even that hard to show. So if you want to take the direction u, you just find it in dot product with the gradient, and it will tell you what's the rate of change in direction. And you know that Oh, this should be a normal vector of length 1. So,
are you projecting the gradient with you, or when you say that you're finding?
Oh, so let me just write it. So you look at. Okay, I have to draw something. Okay, assume that this is our function. It looks like. Let me just find it. Okay, so we have a function that's called x2 plus x1 plus x2. So this is f of x1 and x2. Okay. We want to this we are moving. So this gradient would be what? The first thing that we have to do. This gradient would be derivative with respect to the first one, 2x1. Then the derivative of this one with respect to x1 would be 0. So it becomes 0. Then derivative of this guy with respect to x2 is 0. Derivative of this guy with respect to x2 is 2x. So it would be 2x1 and factor of 2. Okay, so this would be its gradient. So the value of gradient, let's say at point 5 and 2, would be what? It would be 2, 5, 2, which makes it 10. So this is the value of gradient at 1. Now, now let's see if we want to go in the direction of the gradient itself. Okay, so this is a vector. We want to go in that direction. We want to see what's the rate of change. Okay. It's a very valid question. So it's like that. This function looks like what? It looks like, I drew something which I'm not sure what it looks like. Can anybody help me with this? What does this look like? Yeah, thank you. Looks like this. Looks like this. Okay. Now, I'm standing at point 5, 2. 1, 2, 3, 4, 5. Some point here. Okay. Now, there are billions of directions that I can, infinite number of feet that I can move, and I want to see what's the rate of change if I move in that direction. So if I move, I told you that if you want to move a direction of u should be a vector of length 1, just a vector. It shouldn't have length. It's the rate of change would be u dot product with gradient of that. Okay. So let's say we want to change in direction of 1, 0. It means that I'm standing here, I want to see what's the rate of change of function if I just go this way. Okay. Well, not that way. Here. In fact, if I'm on 5, 2, I want to go in this direction. I want to go a little more and see how much did the function value change. Is it clear or not? This is a little bit hard to imagine. So you're standing at this point, which is 0.52. Function has a value of them. Now you want to move in this direction. Make it 5 plus epsilon and 2. Function would have another value. You want to see how much this value changed. So it would be the dot product of the gradient and 1, 0. So it would be 10 or transpose dot product 1, 0. So it would be 10, 10. So if I can be nearly, so if I have 5 plus f, so the value of the function at 5, 2 would be 25 plus 4, which makes it 29. Now if I move epsilon in that direction of 5, so go to 5 plus epsilon and 2, the value of my function would be 29 plus 10 epsilon. Is it clear? So it showed me that if I go in the direction of 1, 0, the value would be. Now if I go in direction of 0, 1, it means that instead of going to 5 plus epsilon and 2, I go to 5 and 2 plus epsilon. Then the value of this guy would be 4. So my function would be 29 plus 4 epsilon. So the rate of changing, if I can change this coordinate, is faster than that. Now I can go in many different directions. The direction that will give you the maximum change would be the direction of gradient itself. That's it. And I'm just thinking I'm not sure if you would really encounter this here, but you might see it later. Don't worry about it. Just wanted to say that this gives us a lot of information, this grid, and it does for that. So this would be the most of the things that I wanted to review. Now, is there anything that you want from the last class that I want to emphasize more?
Second,
Sorry?
second dimension.
Oh, it's exactly the same. Good. It's exactly the same thing. There's nothing different. Let's just write it down in that. Good. So, just think of it exactly what we did here. If you have a vector now x is a vector. I will drop this vector plane because I just don't want too much of it. So it's like, so this means it's x1, x2, plus delta 1, delta 1. They are not necessarily equal. If you want to see how much is the change. So it's f of x plus sigma round up f round up delta I multiplied by delta I. So we are taking the derivative in this direction multiplied by this. Taking the derivative in this direction multiplied by this. This is just like. Now, instead of writing it this way, there's a nicer way to write it gradient of f. This is gradient of f is the vector of this partial derivative. And which way you can transpose delta. Delta is the vector of deltas, and this is the vector of the. So this will be the first order Taylor expansion in more than one dimension. The second order Taylor expansion is exactly the same way as the first order. So if you expect something like the second derivative of x divided by 2 multiplied by a quadratic term. Okay. And it would show if you just write it down exactly for each coordinate. You can write it down for each coordinate using the first one, using the normal Taylor, and then you have to rewrite it the way I did. So if first you write it down, it would be half of all the mixed derivatives, xi, xj, delta I, delta j. This will be just writing it down for each coordinate. And then you can rewrite this nicely, and so this matrix thing is nothing but rewriting it in a compact. There's no magic happening here. Half of delta transpose and so where is the second order term? It's delta, delta, and this is the second order. So this will be the equivalent of the first of the Taylor series in more than one dimension. It's exactly that. Nothing the same because you can just write it down in every direction, add them up, and then write it down. And taking the derivative, you can just, if you really were clueless what to do, write down this matrix, take the derivative, and then make it compact again. Or if you just want to remember, you just drop one of these elements.
Could you
Sorry.
just repeat this? Multi-dimensional.
Explain it again?
Yeah.
Let me just say something. So, what I said was that we are looking at the forget this one. Just the first order approximation, which we are approximating it to the line in one dimension. We had this guy, we approximated it to the line. Now in 2 dimensions, we have a 2-dimensional curve. Okay. And we would, at any point, we would approximate it with the plane. Okay. Nothing more. So instead of going on the curve, we go on the plane. In 3 dimensions, then more than dimensions, more than it, of course, I cannot draw anything for you. So the idea is to just approximate it with a plane line, or a plane, or a hyperplane, something of order 1. Delta, not delta to the power 2, delta to the power 2. So the idea is in the 1-dimensional case, you just said that we take the f of x equals f of x0 plus f prime of x0 x minus x0. Okay? Now, instead of, but now we are saying that the contribution x is more than one, which is a certain is a collection of different coordinates. So each of these coordinates will have a contribution like this. So this f of x is just f of x0 exactly as you see that. Now the contributions are like this. We know that contribution of this one is a partial derivative. So the partial derivative of that one multiplied by the epsilon that we moved in that direction, plus the partial derivative of the second one is one here. So put the sigma here over. So this would be nothing more than just saying round of f to round of delta 1 multiplied by delta 1 plus round of f over round of delta 2 multiplied by delta 2. Delta 1 is nothing more than our x minus, it would be the second coordinate of x minus the second coordinate of, the first coordinate of it was the first coordinate, just coordinate wise. So then you add it up. So this would be the approximation using a plane. Now there we also had a second order approximation which was using approximating with a quadratic function. Now we are approximating with a quadratic plane. So it would be exactly the same concept. The proof is just messy, nothing more than messy. We can just write down exactly the second order for the one direction, and then we need to do direction. It's just messy. If you want, I can do it on paper. So we write it down to this term, and then to write it nicely, we define the function. So then we define the matrix. Maybe I should understand this correctly. So this is what we did in class. There was something we said about so this is what we define the function. So this is the Hessian matrix, just the matrix of mixed derivative of. So we define this matrix, put it here, and these are vectors, just to write this thing. So that's where this guy comes from. So instead of, so we had the first order approximation, which is this, plus this. The second order is this, plus this, plus this. It's exactly like the Taylor expansion for all. Yeah.
Never mind.
Where this comes from is really nothing. You can just write it out. Okay, if I draw it, if I was good at drawing pictures, I could have easily drawn it. It's like this, that okay. In fact, you start at one point, you go a little this way and a little this way. In fact, you're just getting a rectangle of delta and delta thing. It's not that really important. Just you have to write this a small thing that you can. You won't need really, like, you will always have it and just use it. And one thing that I forgot, for nearly all nice functions that we know, the order of taking partial derivative is not important. There are very few cases that might be important. Nobody's done it. So just go ahead. Don't worry about the order. Take this one first and this one. No question? Good? Have a good day.